Welcome. So this is third lecture on quantum mechanics. So in the last lecture we have discussed many things. So now we will continue. So in the last lecture we have discussed about wave function in position space, momentum space, and then quantum postulates, Schrodinger equation, time independent, dependent Schrodinger equation we have discussed. So today we will continue from there. Conservation of probability we also discussed. So we will talk about little more about conservation of probability. So this is what we have discussed in the last session. Let's continue from here in this session. So first of all, the most important thing in the wave function is normalization. Normalization of wave function is very important. Wave function should be normalized. That means for one dimension system, the wave function probability density should be equal to 1 if it is integrated, and if this condition is followed, so wave function will be called as normalized. So for an example, if I talk about a wave function psi, which is a exponential of minus alpha x square, so this would be normalized or not, then we have to calculate the value of a. This is called normalization constant. Normalization constant. So we need to calculate this normalization constant value. If it is given in the examination in the question paper, so you should always check. Okay, sometime it may be given different. Okay, so you always check whenever you do a question related to the wave function that the wave function is normalized or not. So to check the normalization condition, the very important thing, first of all, you should know the psi square value. How to get that? So this is simply psi star psi. So here you have psi as a real function. You see there is no iota, so psi star will be also similar. Okay, so when you do the psi star of this given wave function, it will turn out to be a star exponential of minus alpha x square. There will be no change in the exponential part. So its conjugate, this is called the conjugate of psi star. So now you can easily get psi square, and then you can put in this integration, and that value should be equal to 1. So here we need a standard integration. So I hope that everyone knows this simple standard integration value as root pi by alpha. So with the help of this standard integration, we will calculate the normalization constant a in this given wave function psi. So from here, if I put the psi star and psi value, I will get psi square simply as a square exponential of minus 2 alpha x square. So now we just have to integrate it in the entire range of the x. That should be 1 with the condition of conservation of probability, you can say. So if you solve this, you will simply get a square as 1 over value of this integration. A square is a constant, so it will come out from the integration, and then with the help of standard integration, in the last slide I wrote, so with the help of that you will calculate. So it will turn out to be root pi over alpha, but here alpha is 2 alpha. Okay, alpha means the constant with x square simply. So here also alpha I have written in the standard integration also alpha, so this is similar. But when you do the psi square, we are not integrating psi, we are integrating psi square. So here it become minus 2 alpha x square. So the constant with x square become 2 alpha. That you have to just write here. So a square is coming as root 2 alpha upon pi, and if you solve a value, that will turn out to be 2 alpha upon pi power 1 by 4. So this is your normalization constant. This is the simplest way of finding the normalization constant of any wave function. So now here our wave function become 2 alpha upon pi power 1 by 4 exponential of minus alpha x square. So this is the entire wave function which is normalized now. So this will be called as normalized wave function. So do write this quickly. Somebody writing can pause the video and then further proceed. So now how to draw the wave function, and the wave function when you do the conjugate and find the probability density, that also you can draw. So here this is your wave function. When you get the psi square, you simply draw that also. So this is I'm giving you as a your homework. So you have to draw both the psi and psi square, the probability density, in your notebook. Okay, so these curves are also very important. Now I will be discussing another example that we need to normalize. So for example, if I take psi as a sin x, so can I normalize it? Is it normalizable directly in the entire value of x minus infinity to infinity, or this is not possible to do? So simply we will proceed with psi star, which is the complex conjugate of psi. Now you simply have to find out probability density psi square, so that will turn out to be a square sin square x. Now we need to integrate it. So suppose first we do for the entire space. That should be equal to 1. This integration value should come 1. If it come once equal to 1, then we can say that wave function is normalizable. But here the problem will come when you integrate this thing. This will not be possible. Okay, when you do the integration of sin square x, basically that will not come in the range. So then what to do? Here you cannot get the integration for the entire range of x minus infinity to infinity. You will never get the value of a. Okay, you are not able to find the value of a. So then what to do with it? How to get the value of this particular thing? So for that there is a particular concept of box normalization comes in the picture. Very important thing, box normalization. So basically here you will not go for the entire range. You will confine it in some particular range. Let's suppose here from minus L to L or 0 to L. You can confine your system. So you will not go for the entire range of the X. You confine itself to a particular length. So that is called basically the box normalization. So you can choose your length accordingly, but now box normalization is possible here. So in that case, you can simply integrate the function and get the value of normalization constant a. So we will do that in another example. Before that, I will go suppose for another example, which is like psi is equal to a exponential of iota kx. Just suppose this example we take. Then how we will get the value of a, and is it possible for us to get the value of a? Let's see. So now we take the wave function conjugate psi star. Here you see this is a complex function exponential of iota kx. So when you do the complex conjugate, it will turn out to be minus iota kx. And now if you take the multiplication of both, it will come out to be psi square, simply a constant value a square, nothing else. So now when you integrate a constant value from minus infinity to infinity dx, that should come equal to 1. But a square, when you find the integration of minus infinity to infinity dx here with 1, that will be 1. So here if you integrate, as we have seen here and here also, if you integrate it will come x. So minus infinity to infinity, again it will not give you value. So this will turns to be infinity. So a square is not possible here to find. So then what to do? This integration goes to infinity. Okay, when you integrate it, one integration is x and then so on. But again, same box normalization if I apply, that means I will not apply the limit from minus infinity to infinity for this particular wave function. I will confine it to some particular value from minus L to L, or 0 to L, or any other value. Then it is possible to do. Okay. So let's do these things now with the example that how we can do. So again, same example for sine x. Now I will change my wave function psi is equal to a sine x, but now I will change the limit. I will keep this wave function only for a particular limit. Suppose this is sine function, so I will change it to a particular angle value. Okay, so suppose take 0 to pi only. Okay, and then 0 otherwise. So if it is the case, only from 0 to pi, this function is here a sin x, and otherwise it is 0. So now if you do the calculation, you can easily find out the value of normalization constant. So here if you do the integration from 0 to pi only, a square sine square x dx. So in that case scenario, we simply have what is sine square x integration from 0 to pi only. So that will turn out to be a square here divided by 2 x minus here sine 2x will come divided by 2, and the integration is from 0 to pi. So this is the simple integration of sine square x, and that should be equal to 1. And now if you put the value from upper limit and lower limit, you will get the lower limit 0, upper limit you will get pi, and then here 2 pi is 0. So here you are getting a square by 2 multiplied by simply a pi value, and that should be 1. From here you can calculate a value easily, which is coming as 2 over pi in the root. See, it is very easy to calculate now. So psi x will come out as root 2 upon pi sine x. This is our normalized wave function. Normalized wave function. Simple. Similarly, you can do the box normalization for the. So this is basically called box normalization. You are simply doing the confinement of the range. You can do for exponential of ikx also. So that I hope you will do. I am giving you the next example which I did here as a homework. Okay, so you can take the range. If I give you, you can take the range from 0 to L here. Okay, the range you take for x as 0 to L only, and then do the box normalization. If somebody does not get the answer, you write in the comment box. I will discuss in the next class if somebody want to understand. Okay, so find the answer and put your answer in the comment box also. Do the normalization with the range 0 to L for this particular wave function, and write your answer in the comment box so that I can see. If somebody write it correctly, I will reply that, and so that anyone else having any confusion will also understand. So this I will discuss if somebody has a problem in the next session. So you will just put the comment section and write about it. Okay. So you always make sure that you write everything. So you can pause here and just write. I'm moving forward for the next thing now. So after doing all these things, the very important thing is coming Hermicity of Hermitian. That any particular operator is Hermitian or not Okay, that if we need to find out what to do. So stationary state we have discussed, and I will also discuss little more about it in the upcoming topic. But you have any stationary state, suppose, then a simple criteria it will always follow is that integration of the probability current density over the entire time range, that should be equal to 0, and this comes out to be dt psi d psi star over dt in the data. So this is a very important condition for a stationary state. Here, rho RT is simply your, you know, the probability. Okay, this is simply probability density. Okay, so now we will establish some relation with probability current density, Z also, in the next topic. But first, I will talk about the Hermicity of a Hermitian, which is very, very important. So now let's discuss. If I have a wave function psi, what is the basic use of wave function? We will apply the wave function psi to any particular operator. I can have a operator like Hamiltonian or a operator like momentum. So we apply a wave function to any particular operator and we find the information related to that what that operator is going to do with the wave function, how the wave function is going to change. Okay, all of the operator will change the wave function accordingly. Okay, if you apply a momentum operator, if you apply a Hamiltonian or any other operator, they will work differently. So suppose I have a operator Hamiltonian H, and if I apply it on a wave function psi, so what is the value of this operator H? This is energy operator, so everyone knows that its value is iota h cut d over dt. Okay, and we have applied a psi on it. So what will be its complex conjugate? Its complex conjugate value will be h psi star, the complex conjugate of this side. Iota h cut will convert into minus d over dt psi star. This will be the complex conjugate. And now, if this is a stationary state, this will always follow this condition. Okay. So in that case scenario, if we apply the psi d psi here, you see d psi over dt, d psi star over dt here we have. So if we put these values, we'll keep this psi star and psi as it is. So now what format we are going to get? So in the entire range of V, we have here from this definition of stationary state, psi star d psi over dt. D psi over dt we have from here, so we will choose it accordingly. S psi upon iota h cut. What is the value of d psi over dt? H psi upon iota h cut. So this I can put here psi star multiplied with h psi over iota h cut, and further we have is plus psi, and here we are getting is h psi star over negative of iota h cut over negative of iota h cut. So this we have, and d tau is equal to 0. Now here you see an interesting thing, iota h cut will go to 0. So what we are getting is in the entire range of the integration psi star h psi, here we have minus sign, so minus psi, and then we have here is h psi star. Okay, theta, that is equal to 0. So we can separate these both. So integration of psi star h psi, that should come out as d tau, negative will go become positive, psi h psi star d tau. Okay, This is the basic definition for an operator to be Hermitian. Definition of Hermitian operator. You can find any operator is Hermitian or not with the help of this simple definition. Okay. Simply here H is the operator kind of thing you can say. So you can replace any other operator. Okay. You can replace it with momentum operator or any other, and then you will find out that is it a Hermitian operator or a non-Hermitian or anti-Hermitian you can say. Okay. Hermitian or anti-Hermitian. So for a Hermitian operator, you guys know very well that Hermitian space is a complex space. So space will be a complex, but what about the eigenvalue? What is the eigenvalue of Hermitian? Is always, I hope you know about this, but if you don't know, you keep it as a very star point. Eigenvalue of Hermitian is always real. Okay, very important point. So write down this quickly. I will give you another example for the momentum operator. So if you want to find out the momentum operator, which is given as simply P is h cut over iota del over del x. Now, here a very interesting thing that you need to find out the Hermitian. So this is the symbol for a Hermitian conjugate. So if you apply this h over iota del over del x, so h over and iota is constant, and if you do the complex conjugate, here it will come with a negative sign, and here del over del x dagger. So this is representing the Hermitian. So P dagger will be Hermitian if del over del x is anti-Hermitian. Okay, very interesting thing here. We will just look for the del over del x now, and if we do that, then del over del x if comes Hermitian, then you will say that del over del x Hermitian is del over del x. There will be no negative sign. But if come, then if it is Hermitian, then there will be a negative sign if you do a P dagger. Okay, then you will simply say that P is not Hermitian or anti-Hermitian. So we have to find out the value of del over del x. So we have to check for del over del x to be Hermitian. What is the condition that it should follow? Here the definition we simply have. So we are dealing with in the one dimension only. So this integration limit we will take in 1D with the integration range from minus infinity to infinity. So we have the definition simply psi star h psi. Here we are taking h is kind of any operator we can take. So del over del x is our operator psi dx. So this I am just doing here in the definition. Instead of h, we are putting del over del x and just writing in the limit. That should be equal to, now here we have this entire range. Here also you put the v. So psi h psi star. So we have integration minus infinity to infinity psi h psi. H psi means del over del x is over h. Now here, not exactly the h value you put, you just put the new operator del over del x. And here we have psi combined and the complete star, the conjugate of this value. So now we just simply have to integrate and solve this side, and we should get equal to this side. If it come equal, then we will say it's a Hermitian. If it come with negative sign, it will be anti-Hermitian. So you have to simply take as a first function and second function, and then you have to integrate it. So first function and second function you do and integrate it, the simple integration will come. So here differentiation, so it will integrate it, then only psi star you are getting, minus infinity to infinity, then minus integration, minus infinity the range. Then you have here is the first function differentiated del psi over del x. Then you have integrated the second part, so only psi star you get here and dx. Now when you solve this portion, this is from minus infinity to infinity, so it will go to vanishing mode. So the other side here we have is this one. So you see, this side is similar to this, but coming with a negative sign. So you see, minus infinity to infinity. Here we have is del psi over del x psi star dx. So you see. So how this is minus infinity to infinity. So wave function will vanish. Wave function will vanish, as we have discussed. For a bounded system, the wave function should vanish. In the last I think first lecture we have discussed that. So if somebody missed that, please watch that how this integration will go to 0, because at the extremities the wave function should be 0. That is the basic thing we have just discussed. So this will be 0 at infinity, psi or psi star both. So that is why this will go to 0. So now we are particularly getting is that the integration of psi star d psi over dx comes out to be negative of d psi over dx psi star dx. So this negative sign is basically informing us that del over del x is anti-Hermitian. Very important point. So that means del over del x dagger, if you do the Hermitian, it will give you the negative of del over del x. So now we were talking about the momentum operator, not about del over del x. So for momentum operator, if we do the dagger for the momentum, P operator we were having is h cut over iota del over del x. So if I do this, Hermitian will come out to be minus h cut over iota del over del x Hermitian. So here we are getting anti-Hermitian. Basically del over del x Hermitian is negative of del over del x, means it is anti-Hermitian. But this negative value and this negative value become positive. So del over del x only. So this is coming P. So here we are simply getting that P dagger is P. So that means P, which is h cut over iota del over del x operator, is a Hermitian. So these are the basic classes, guys. You should understand the basics very well. Then only you will be able to solve hard question very quickly, real fast. So please do write this quickly, and then we will proceed to the next thing. So the next topic will be of another importance. That will be also very important topic. So that I will be discussing in the next session only. Okay, this class I will keep till this point only. So here in this session we have basically understood two main points. One is the normalization of a wave function, which is quite important to do. Okay, in the any equation related to the wave function, always do the normalization, the first necessary thing to do. Then only proceed with the further solution. So here we discussed about the wave normalization. Box normalization, that means the wave function which you cannot normalize for the entire range of the space, you will cut down the limit of that particular space, or you will range the function, and then you will only do the normalization. So here I have given you this homework. You please comment down your answers so that we will discuss. Another example we discussed. Then a very important topic, Hermicity of Hermitian operator, that how to get the definition. This stationary state definition also I will be talking about in detail in the next session. But first For the Hermicity of Hermitian, I just directly told you this thing. And now with this, we have discussed the definition for Hermitian operator, which is very, very important. Okay, from this, there will be a question in the GATE exam and CSIR exam also. Directly, you will be getting the solution, and it is very important. Directly can be asked in IIT JAM with the definition only, that what is the definition of a Hermitian operator mathematically. So these are the some example we just discussed. So with that, I am ending this session. So this third session is ending, and this will be live session. So you please put your comments and solve these things also. Okay. So for the solution, I will upload if anybody get doubts. So this is what we have only for today, and then next session I will upload soon, and you will get the further concepts. Thank you. See you in the next classes.